Okay, hello class. This is weekly update 2. So a couple general announcements. Got a few emails about the quizzes, and thank you for the notes that you put in Oaks regarding your quizzes. I noticed that, and Chloe reminded me of this, that there is a way where I can go in and show incorrectly the ones that you've gotten wrong. So it makes it easier for you to understand what's going on. So I believe I've done that for at least the next couple. Let me know if I still haven't done that. So hopefully that'll help you out. And then the other thing on the quizzes, this was also another great suggestion related to one of Chloe's emails. I'm going to post, your textbook comes with the solutions chapter by chapter. So once we finished chapter 1 on the quiz, I went into Oaks just right under the quiz. So I think it's the only thing you have is course materials and assignments. So under the assignments, it'll say quiz 1. And you go ahead and thank you for uploading your work, folks. That's also helpful. If you happen to do poorly on a particular quiz, I can look at your work and adjust your grade, and I will do that accordingly. And then under that, so you submit your work, and then under that, there will be chapter 1 solutions posted. And these are all the problems worked in Rardin. The answers are there. So I just did that for chapters 1 and 2 because you finished quiz 2, and we'll do that every time we have a quiz that completes an entire chapter. We'll have that, and that'll help you study for your exams. So remember, our first exam is September 27th. We'll have chapters 1, 2, and 3 done by then. Chapter 3 you're really gonna like. That's fun. We're gonna start getting into some really good algorithms and the overarching theme for when we get to the simplex. Okay, oh, also thank you to Kristen. She sent a couple emails. She's already kind of started an errata for this Rardin textbook. So this is the second edition. I waited, I have been using the first edition all this time. Award-winning, great job. And he made an excellent errata that he kept up to date, and you could download, you could easily find this and download the file and see, okay, well, that seems kind of weird. And he would say, you know, I made a mistake on example 1B on page 36, and you'd go and see if it was there, or the exercises that do at the end of the chapter. And so Kristen's already found 2 for the second edition. Unfortunately, I haven't been able to, maybe some of you are better Googlers than I haven't been able to find an errata. And it could be because the book just came out and he's working on it. It could be I haven't found it. Or it could be that he's getting closer to retirement. But she's already found 2 errors. So the one I believe was like in the text in chapter 2, I think it was number 8, example 2.8. He was trying to compare a unique solution to a polytope, an LP with multiple optimal solutions, and the 2 problems were exactly the same. Like he didn't change anything. So Kristen noted that, and we've had some correspondence. So if you were asking about the same one, either shoot me or Kristen an email, and we can send the response. He meant to change one of the coefficients on one of those. And so I think I was able to work backwards and figure out what should have been. The second one Kristen noticed was number 42 at the end of the chapter. So chapter 2, 2-42, that exercise, the labeling of the coefficients and the variables doesn't make sense. His indices are off, and they're actually copied from the first edition. So it's easy to see how these errors creep in. So if you as a class can keep a list of those, he would love to see these. We'll email him at the end of the class, and we'll just keep adding them to our errata list. So the moral of that story is thanks to Kristen, first of all. And secondly, sometimes if you're racking your brain over something, this doesn't seem to make sense. There are errors and there's typos. And as an author myself, I see how that's easy, how they happen despite your best efforts, and they can creep in. Okay, let's then go to your group assignments this week. So again, I will be the conduit, which brings all the different ideas that we've had. So I'll just talk about a few of them, and then we'll screen share some of them. So Noemi and Olivia L, they had a couple methods that were like, hey, this is like a vertical cylinder, easy formula. Maybe I will dig out the dirt and fill it with water. They had a couple of these water displacement type ideas. The group of Chloe, Michael, and Olivia S, again, did a, hey, it kind of looks like a vertical cylinder. They seem to have really nice teamwork in their write-up. I appreciated that. And they played many different roles, that they all wore the different hats of, sort of devil's advocate, task organizer. But most of their ideas had to do with Riemann's sum. So they probably had, I don't know, maybe half a dozen different ideas that were all plays on Riemann sums. So they take a look at this, the shape and said, actually, maybe it's more of an elliptic cylinder, and we'll take horizontal slices, or we'll take vertical slices, or we'll just shove different shapes in there of which we know how to compute the volumes of each of those. Okay, and then Kevin and Jenna, I think Preston had some issues this week, so it was just Kevin and Jenna. They also had a bunch of Riemann stuffing ideas, and I also appreciated Kevin had a ton of list of questions. Like, again, if I'm actually working with a client and trying to do this, I would go back and I'm curious about these sorts of things. And then the group of Zach, Andre, and May, they had several, so many of the ones that were already discussed, water displacement, volume stuffing ideas, Riemann ideas, but they did a neat thing where each of their methods, I think they also had maybe half a dozen different things. They scored each one on like accuracy, tractability, feasibility, computational effort, and they talked about things like memory and cost, all these things that if you really are a company, like, oh great, you have these ideas, but what's the one that you're actually going to be able to implement? Which one do you have the computational resources to do? And several of their models were, they actually talked about scaled down 3D versions of this, that they then put in a computer. They had software that would, sort of AutoCAD draw all these things, get dimensions. So they had several virtual and 3D models. It's a really wild method. So maybe we'll share the screen real quick and show a couple of those. Let me see if I can find it. Where did I put those? Yes, okay. Okay, so again, here's their these things. They gave a score to each of these and discussed feasibility, tractability, accuracy, speed, computational issues, and rated all their methods. They did a water displacement one, worst one, all the way up to again Monte Carlo methods for volume estimations. Neat idea there. Some more volume ones. They got more and more intricate, I think, as we went up, like triangularization, filling this thing with a bunch of triangular simplices. Oh yeah, brute force, just using a formula. Oh yeah, this is a pretty wild one. These ortho schemes that they were talking about. And I think there's, oh yeah, isosurface stuffing, another type of stuffing, like a Riemann type thing. And then just looking at the architecture, they noted that there's some professors that have done quite a bit of work and have copied the records, and then they could really do an analysis looking at this, the detailed plans. Okay, then another group, Brianna and Avery, they noticed, many of you said, okay, well, it's more like a vertical cylinder, but or circular cylinder. They said it's elliptical. They talked about the water displacement. They talked about Riemann boxes rather than just any shape. They just talked tiny little cubes, maybe they would put in there. And then they did this probabilistic approach. Let's pull theirs up then. Let's see. So this is a Word file. Yeah, okay. Oh yeah, so here's like their battleship. They just said, let's assume it's elliptic cylinder. I'll calculate the height and just need to get the area at the top. And they did this probabilistic idea where they're just dropping things and seeing whether it hits or misses and getting a area at the top times the height. And then this other one was slightly different. A lot of people did some water things, but they actually surrounded this one that's slightly more feasible than other people. Like, hey, I'm going to dig out. This is the culture. I'm going to dig that thing out. Volume of the tank and minus the amount of water they added gave you what's left over. So again, this sort of complementary idea was a really clever way of thinking differently. Okay, and then last one was Ashley, Maddox, and Kristen. So let's pull theirs up. So share for a minute. Go back to. Okay, so these guys made a nice report. This is, I learned, I had no idea. So here is actually the cistern. I think Jenna, being new transfer student here, was thinking it was actually Randolph Hall. And sometimes in the past, people think it's the entire cistern yard. So they're getting like a rectangular measurement. But when I was saying, I actually meant this like elliptical oval thing, but they show what's actually happening underneath. I forget, where did they get this? They mentioned where they got this figure. And so they're actually talking about these chambers underneath. I had no idea. I learned that. Most of you thought it was just the top. So, but this is a different way of looking at it. Given that there's these chambers, they had to make different assumptions. I think they have 4 different methods here. And each one, they make an assumption, assuming maybe this is solid or this water can actually go through there. And lots of, typical calculus using formulas, some Riemann slices that they took in here, I think. Yeah, some heights, different chambers, whether they're loaf-shaped or cylindrical. So again, all these are along the same vein, which was why it was neat to see the different groups, how much variety. And I think in terms of like variety and creativity, I really liked Zach, Andre, and May, and Brianna and Avery. I felt like they had the wildest difference of ideas. And that's what I was wanting in the brainstorm session. Just take 20 minutes to brainstorm, just throw out anything you can, and then take a longer amount of time to sort of analyze and dissect those. All right, so I hope you had fun with that, learned a little bit more about your groups and different ways that different people think, and when we're creating algorithms for a client. And again, I think chapter 3 is going to be fun, so enjoy.